Okay, welcome back to part B. So let's go ahead and just a quick review of this problem in case you put a little space between these videos. So this is number 12 and they asked us to find the horizontal asymptote for h of x equals x squared minus x minus 6 over x squared minus 4. Okay, now we looked at this one earlier to use it to define the idea of what a hole was. But here they're asking us to find the horizontal asymptote. And again, you do that in the unreduced rational. You don't reduce it first. So finding the horizontal asymptote here means, again, as we looked in the previous examples, we take the ratio of leading coefficients. Now, why do we do that? Well, because we see that the leading term in each of the polynomials, oops, my bad there, excuse me, has the same degree. In other words, they're both x squared. So we know that y equal to x squared over x squared is going to give us the equation of the horizontal asymptote, or y is equal to 1. Okay, and again, I'm going to let you go ahead and use your calculator or Desmos to show that indeed that is the horizontal asymptote to this function. I'll let you do the graphing part because you got to have some fun too, right? Okay, so let's slide forward and talk about what the main topic of this video is, which is intercepts. So as with all functions, and in particular with rational functions, we want to find, does the function have a vertical intercept and does it have a horizontal intercept? And how we go about doing that turns out to be very similar to what we've done in previous functions. For a vertical intercept, we know that the input has to be equal to 0. In other words, if we want to know what the y-intercept is, the vertical intercept, that infers to us that x must have been equal to 0, okay? For a rational function to not have a vertical intercept, it's the only way that's going to happen is if it's undefined at 0. So a rational function won't have a vertical intercept if it has a vertical asymptote or a hole at the origin, right? So in other words, if it's undefined at 0, in other words, we put 0 into the function and we get back division by 0, then we know it doesn't have a vertical intercept. Otherwise it's going to have a vertical intercept. Okay, horizontal intercepts, how do we find those? Okay, so remember, horizontal intercepts are where we're crossing the x-axis. And so if we're talking about an x-intercept, then we know that what must have happened was that y was equal to 0, or was the output, or the functional value must have been equal to 0. So likewise, a rational function will have a horizontal intercept at inputs that cause the output to be 0 unless input corresponds to a hole. It is possible that there are no horizontal intercepts. Since a fraction is only equal to 0 when the numerator is 0, the horizontal intercepts occur when the numerator of the rational function is equal to 0. Okay, so that's actually a handy little thing. What that basically says is this. We have the zero product property. It says if you have the product of two numbers is equal to 0, or product of two items is equal to 0, then one of them must have been equal to 0 in the first place. Well, there is a zero quotient property that says if you've got a divided by b is equal to 0, in other words, if your rational is equal to 0, then the only way that that could have happened was if a was equal to 0. And simultaneously, b is not equal to 0, all right? It's got to be defined at that point too. All right, so let's go see if we can put all this stuff to work. So for each of the function, find the horizontal intercept, the vertical asymptote, the horizontal asymptote, and use this information to sketch the graph. Oh, okay, so let's do that. So they want us to find the horizontal intercept and the vertical intercept. So the horizontal intercept, well, the horizontal intercept is what? That's the same thing as saying what is the x-intercept, because that's the horizontal axis, which infers to us that what? It says that, well, then k of x must have been equal to 0. We're going to solve that equation. So we're going to say 0 is equal to 2x squared minus 3x minus 20 divided by x minus 5. Okay, now we just discussed, we said the only way that can be true, the only way that we can have this function be equal to 0 is if this part, the numerator, was equal to 0. So in order to find the horizontal intercept, excuse me there, sometimes when I touch that thing, it freaks out. I don't know what it is about it, like it runs away from me. Okay, anyway, back to the rancher. So if we want to find the horizontal intercept, we simply have to set the numerator equal to 0. So that says, or infers to us that 0 is equal to 2x squared minus 3x minus 20. Let's make that look like a minus and not a multiply there. Alrighty then, so if the gods are with us, this will factor. Let's see if it does. We take about 30 seconds to try and factor it, and if it doesn't factor, then we'll use the quadratic formula on it, okay? So let's see, 2x and an x, and then we've got a minus 20. So 20 would be what? 4 and a 5. So let's see, if I put a 4 over here, put a minus there, and put a plus here, and put a 5. Let's check that. That gets me 5x minus 8x, which gets me negative 3x. Yep, it factored. Okay, sweet. So now I can go ahead and use the zero product property here, which says that 2x plus 5 is equal to 0, or x minus 4 is equal to 0, which says that x is equal to negative 5 halves, or x is equal to 4. So those are my two zeros, which gives me the intercepts are going to be at negative 5 halves by 0 and 4 by 0. Okay, so so far I've got the horizontal intercepts. So let's put a check mark next to that one. Done. Okay, vertical intercepts. All right, let's partition off the paper here so we know what's what. So vertical intercepts, which that's inferring to us is that we want the y-intercept, which infers to us that what we need to do is make x equal to 0. So that means we've got to go find out what k of 0 is equal to. Well, k of 0 is going to be equal to what? 2 times 0 squared minus 3 times 0 minus 20 over 0 minus 5, which is going to get you back what? 4? If I evaluate the numerator and the denominator. So that tells me that the ordered pair 0, 4 is my vertical intercept. Okay, now they want the horizontal asymptotes and the vertical asymptotes. Okay, so, well, fortunately, we've already put the numerator in factored form, and we see that there are no common factors between the numerator and denominator. So that tells me that finding the vertical asymptote is simply going to be finding the denominator set equal to 0. So let's get a clean piece of whiteboard here to do that. So I'm going to rewrite it in factored form just to make clear what I just said. So we've got k of x is equal to, let's see, what was our factored form again? It's 2x plus 5 and x minus 4 for the numerator. Okay. And then in the denominator, we've got x minus 5. Alrighty, so what do they want from us? Oh, they want the vertical and horizontal asymptotes if those exist. So let's go ahead and do the vertical asymptote first. I'll abbreviate that as VA. Okay, so the vertical asymptote, what happens there is that's when the denominator is equal to 0. So that's x minus 5 is equal to 0, which says x equals to 5 is the equation of our vertical asymptote. All right. Now the reason I left it in the factored form here is for you could see that there were no common factors between the numerator and denominator. All right, now that's good, but leaving it in the original form where it was all multiplied out is going to be much more useful for us with respect to the horizontal asymptote because we got to check the degrees. So let's see, in unfactored form it's 2x squared minus 3x minus 20 in the numerator. Over my x minus 5. Okay, and now what we're going to do for the horizontal asymptote again, what we need to do is look at the leading terms. So in other words, only the highest degree term in the numerator and denominator come in for dealing with the horizontal asymptote. So let's go ahead and do that. So if we take a look at that, we see, let's get the color here, we would have what? Y is equal to 2x squared over x. In other words, grab those leading terms, form the ratio, and we get y is equal to what? 2x when we reduce that. So it does not come to a constant, it comes back to a function, which is kind of useful information because what it tells you is in the long term, it's actually tending towards this line, y equals 2x, but it doesn't have a horizontal asymptote because that's not a horizontal line. So there are no HA or no horizontal asymptote. Remember, horizontal asymptotes are always going to be the form y equals b, y equals a number, because it's a horizontal line. That's the equation of a horizontal line. So in this particular one, there is no horizontal asymptote. Okay, now what they asked us to do is to take this information and make a reasonable sketch of it, okay? So let's go ahead and do that. Let's make ourselves a glorious X and Y axes here. Okay, to the pencil. Okay, so let's see, that's going to be the x-axis, that's going to be the y-axis, and what do we know? What's the information that we're given? Well, we're given that it goes through the point 0,4. The graph is going to pass through that point, so let's go up 1, 2, 3, 4. So we know it's going through that point right there. That's my vertical intercept, and then we know it's going through -5 halves 0. So -5 halves 0. So that's 1, 2, 3. 5 halves is basically 2.5. So that's going to be roughly about there. Okay. And then we're going through 4, 0. So plot that point. So 1, 2, 3, 4. So that point's going to be right there. Okay. Cool beans. All right. So we know those are my intercepts. What about my asymptotes? Okay, well, we know we got a vertical asymptote at x equals to 5. So if we go 1, 2, 3, 4, 5, we go right here, we know we have a vertical asymptote, and we know we have no horizontal asymptotes, okay? All right, so how are we going to graph this thing, or what should we do to graph it? Well, we can grab ourselves a couple more points. So once you have got all the information that you know about it, then go ahead and pick a couple more points to help you figure out how to plot the thing. So in this case, let's go ahead and pick x equals to 6 because we want to get something on the other side of that vertical asymptote. In other words, we're going to go find out what k of 6 is equal to. So let's get the calculator in here because I'm going to use that to help me do the arithmetic because we all know how great at arithmetic I am. So let's get the calculator over here. All right, clear it out. And so what that is going to be, actually, let's move it over here for just a moment so I can see what I'm doing. All right. So that's going to be parentheses 2 times 36, which is 6 squared, minus 3 times 6 minus 20. Close the parentheses for the numerator, hit divide, and then open the parentheses, and we know 6 minus 5 is equal to 1. Let's just do that in our head, okay? So we got something there. Okay, so we end up with 34. So we know, let's calculate over here where I want it, and we know that we're going to be at a huge value over here. We're at 34 when we're at 6, okay? Which is like way off screen. It's like way up here. All right, so we know that when we're on either side of the asymptote that we're going to actually be a smooth continuous function. So this function is going to have to look something like this, okay? And we know we came from way up here up above it, okay? And we also know what? We know that we don't hit the x-axis again, which is interesting that we're way up there. So I'm going to punt and go ahead and take a look at the graph here. I tell you, I'm what does this graph look like? Now I'm thinking about it. So let's go ahead and put it in there. So let's go in parentheses. And let's put in 2x squared. 2x squared minus 3x minus 20. Parentheses divide, open parentheses, x minus 5. Close the parentheses, and we'll do a zoom and a standard to start here. Cool, got that part right. Not seen a lot. Oh, I know what's going on the other side. I remember now. Oh, Mr. Cotter, we got to open up our window a little bit, okay? So let's open up the window here. If we open up our window, let's make our y max bigger, okay? Because we know what, we're up by 36 over there. So we're going to need to make it, get it way up there. So let's go for, oh, I don't know, let's say, let's start off with 50. Let's do it that way. What we see is you're going to have basically another piece just like that piece on the left coming up over there on the other side. And so that's what's going on over there. And so really the only way to get that other than looking at the calculator is you would have to plot a bunch of points to help you see it, okay? But we just need a rough sketch of it. So giving a rough sketch, we'll have to be up here, cheat a little bit because we know it's up a little bit different now, so it's going to look something like that in the upper part, okay? And so those are the two pieces of the graph. Rational functions, because they have vertical asymptotes in them and horizontal asymptotes, are not, generally speaking, are not continuous, okay? They have breaks in them where you have your asymptotes. So that means that you need to pick up your pen or your pencil to continue drawing it to get from one piece of the graph to the other one. Okay, let's do another one. So for each of the function, find the horizontal intercepts, the vertical asymptotes, the horizontal asymptotes, and we want it all chocolate coated, okay? Alrighty, so this one, they were nice, at least, and they gave it to us in factored form. So let's go ahead and we'll do them in order here. Let's go ahead and find the horizontal intercept. So the horizontal intercept, that means that we're talking about is the x-intercept. And if we're talking about the x-intercept, that must mean that y was equal to 0, which says that 0 is equal to x plus 2 quantity squared times x minus 5, all divided by x minus 3 times x plus 1 times x plus 4, okay? But we know that the only way that this thing can be equal to 0 is if the numerator was equal to 0. So what we need to solve is you need to solve x plus 2 quantity squared times x minus 5 is equal to 0. And we're lucky because it gave us this in factored form to us already, so that's a beautiful thing. So this x plus 2 quantity squared, remember what that is that's x plus 2 times x plus 2. So we have a root of multiplicity at that point, and that's times what? X minus 5, which is equal to 0, okay? So this gives me that what? X is equal to negative 2 with a multiplicity of 2. And then we also get what? X is equal to 5, okay? So those, remember, those are the zeros. We need to write those as intercepts. As intercepts, that's negative 2 comma 0 and 5 comma 0. All right, great. So that took care of the horizontal intercepts. Let's go take a look at the vertical intercepts. So check-a-rooney on that. Now we're going to go down here to the vertical intercepts. So the vertical intercept, what does that mean? So that infers to us we're looking for the y-intercept. And if we're looking for the y-intercept, that means that x must have been equal to 0, right? Which says what we need to find is what is z of 0 equal to? Well, z of 0 is equal to 0 plus 2 quantity squared times 0 minus 5 divided by 0 minus 3 times 0 plus 1 times 0 plus 4, right? Okay, so that's going to be in the numerator, that's going to be 4 times negative 5, which is negative 20. And in the denominator, we're going to get negative 3 times 1 times 4, which is negative 12, right? Okay, so now what? Let's go ahead and simplify that a little bit so we know it's going to be a positive number. We know 4 goes in evenly to both the numerator and denominator, so we get back what, 5/3? A positive 5/3. So that, excuse me, that tells me my vertical intercept is at 0 by 5/3. Let's partition this off here so we can keep our work somewhat separated out. Make that look like an X. Okay, cool. All right, so we got the vertical intercept taken care of, bada bing, bada boom. Now let's go to the horizontal asymptote. So for the horizontal asymptote, we're looking at the degree of the numerator, highest degree term divided by the degree of the denominator. All right, now this is a little bit tricky because they didn't multiply it out for us. They left it factored form. Of course, that was very handy in the previous work, but it's going to make it a little more challenging for the horizontal asymptote. The thing to realize is that you just need to look at the leading term in each of these binomials and multiply them together to figure out what their degrees are going to be. So notice that this one, the leading term, when I multiplied out x plus 2 quantity squared, that's going to be x squared plus 4x plus 4, but I only need to be worrying about what? The x squared from there. And same thing here, I'm only going to need to worry about that x. So that tells me the numerator, when I multiply it all out, the leading term, the highest degree term, is going to be equal to x cubed. Now, if you prefer, just multiply the whole stinking thing out. It's a little more work, but if you feel more warm and fuzzy about seeing this, then definitely do it that way. But the shortcut is you simply need to just look at the first term in each of these and multiply them together to tell me what the highest degree term is going to be in that denominator. And likewise up in the numerator, of course, you had to be a little bit tricky with the x plus 2 quantity squared. But nonetheless, hopefully you see the denominator is also got x cubed as being its highest degree term. So y equal to 1 is going to be my horizontal asymptote. All right? Hopefully that makes sense. If not, rewind this and watch it again until it does make sense. All right, let's go for the vertical asymptote. All right, there's no factor in common between the numerator and denominator. Seeing there are no factors in common between the numerator and denominator means we do not have a hole, that we have vertical asymptotes here. So let's go ahead and take a look at that. Looks like we're going to have a vertical asymptote at x equals to 3, at x equals to -1, and at x equals to -4. Okay, all I simply did was set each of these factors to 0 and solve them, and that got me the equation of the vertical asymptotes. All right, so we've got that too. We got the vertical asymptote, we got the horizontal asymptotes, we got all the asymptotes. Let's go make a graph, because that's what they really wanted from us. So let's go get the line tool here. Let's see if we can do the graph without having to look at the calculator. But if we do, no worries. I mean, that's the reality of the world, is you would be looking at the calculator anyway before you did this. But we're going to just see if we can figure it out first based on the knowledge. I mean, part of the exercise here is to try and drive home what all of these things are telling you, okay? All right, so let's see. Horizontal intercepts, we've got, what? 2 of them. We've got one at -2, 0. So let's go ahead and plot that one. So -1, -2. So we know we've got that point right there. And we also know we're going through 5, 0. So 1, 2, 3, 4, 5. So we know we're going through that point right there. And then on the vertical asymptote, we're going through 5/3. So that's 1, 2. See, 5/3 is what? It's 1 2/3. So that's roughly about there-ish. Okay, we'll make it big, and that way we got it covered. Okay, sweet. Let's go ahead and change the color of the pen this time. I should have done that in the last one so we can make our asymptotes a different color here. Let's make them purple, what do you say? So, look, any color you want, right? We got all these colors. Let's use them. All right, so for our horizontal asymptote is at y is equal to 1. So put in this dashed line here at y equals 1. And then we've got a vertical asymptote where at x equals to 3. So 1, 2, 3, we've got a vertical asymptote here. And at x equals to -1, we've got a vertical asymptote. Now remember, the function does not pass through vertical asymptotes. We can pass through horizontals, but that's a special case. But we do not pass through vertical asymptotes. And then we've got another one at -4, okay? So -4, -1, -2, -3, -4, and so we've got one right here also. Okay, woof, this is going to be a crazy looking function, isn't it? All right. So what should we do? So I'm going to tell you that what I would do is go get my calculator out again and do this. That's what I would do. Now that we've got all this important information plotted, let's see if we can actually get the graph, okay? So go ahead and clear out whatever you got in Y1, all right? I mean, you can plot a few more points. That is actually what you would really, if you were back doing this in the day when I was taking this class and we didn't have calculators, your next step is to make a table of points, plot enough points that you can use your asymptotes and those intercepts to actually get the graph, which is a viable and a good way to do it if you don't have a calculator, but we have a calculator, so we're going to use it. All right, so parentheses, parentheses, x plus 2, close parentheses, we're going to square that, parentheses x minus 5, going to close that, close the numerator, put in a divide, open the denominator, open again for the x plus 3, and then close that one, and then open for the x plus 1. Then we'll close that, and then open for the x plus 4, and then close that, and then close that. Okay, all right, and now press graph. Actually, let's do zoom and a standard. Let's try that again. So zoom and a 6. There we go. Alrighty then. Okay, so let's see how that corresponds to what we started drawing, all right? Let's move my calculator over here. I had it in the right spot in the first place. Okay, so through the magic of being able to pause my video recording, I discovered that I had made a mistake on the input. So you probably were yelling at me, going, no, Mike, stop, you idiot. Yes, hopefully you were. So that should have been x minus 3 in the denominator. I had put an x plus 3 in there. So ignore that previous graph that you just saw because that was wrong, all right? So I was like, wait a minute, this is not working because I'm not getting the right vertical intercept, and I know my vertical intercept is right. There we go. So that's the correct graph. Okay, so let's go back now and let's see if we can get that to translate into our graph here. Okay, so what do we got? Well, over here in this part of the world, we see, let's switch back to the blue and the color again here, the dark color. So we see that we're trapped between these intercepts. And again, you would have to plot a point to find out where that one was going through, okay? All right, now this point right here, this -2, we know that's a multiplicity of 2, so we know we're going to bounce on that, right? Now, if we think about the bounce, it would be hard to come in. You can pass through a horizontal asymptote, but that's not going to be, that's a special case, okay? We're not going to have that happen to us right now. So we know what we're going to do is we're going to come up, we're going to bounce, and we're going to turn around and go back down. And the reason we know that was because the x equal to -2 is a root of multiplicity 2, right? Okay, so now what about over here? Well, on the next interval, we know we're going to have to come through our y-axis at this point. So we're going to come down, pass through the y-axis, and then come back up again. And then our last piece here, well, we know we're going to come up and then we're going to have the horizontal asymptote, so we're going to come up like that, okay? And yes, indeed, that does agree with our graph that we got on the calculator, okay? Now you can input the lines on either Desmos or on the calculator to see the asymptotes, but that's not really necessary. It's good if you just draw them by hand. Okay, you don't need to see them on the screen is what I'm saying, but it is important when you do your sketch that those asymptotes show up. And it's actually pretty good too if you label them with the equations of the asymptotes. So we know, for example, we know that those vertical asymptotes were at 3, back over here, -1 and -4. So if you came in here and you labeled this as x equals -4 for that asymptote, x equals -1, and x equals to 3. And over here, if you label this one with y equals to 1, that's a little more inclusive and instructive to the people who are reading your graph, okay? If you leave those off, I would not mark you wrong unless they ask for them, okay? All right, writing rational functions from intercepts and asymptotes. What if you're asked to go the other way around? Okay, so if a rational function has a horizontal intercept at x equals 1, 2, 3, etc., and vertical asymptotes at v1, v2, v sub n, then the function can be written in the form as x minus x sub 1 raised to the p1 power, x minus x sub 2 raised to the p2 power, x minus x sub n raised to the p to the n, p sub n, okay? Where the powers p sub I and q sub I down in the denominator, just repeat the whole thing I said again in the numerator and the denominator, and each of the factors can be determined by the behavior of the graph corresponding intercept or asymptote. And a stretch factor A can be determined by given a value of the function other than the horizontal intercept or by the horizontal asymptote if it is non-zero. In other words, just as before, I can tell you the equation if you give me a single point. I can tell you what that factor A is going to be. In other words, give me a value that I know is on the function, and that will do it. All right. So what that means is, let's go ahead and get started. We'll do number 20, and then we're going to call it good in this video. It says write an equation for a rational function with the given characteristics. So it's got a vertical asymptote at x equals -4. And at x equals to -1. It's got intercepts at 1, 0, and 5, 0, and it's got y-intercept at 0, 7. Okay, so now let's go back up to see if we can breathe some life into what I just said up here. So if you have horizontal intercepts at x equals x sub 1, x equals x sub 2, etc., and vertical asymptotes at x equals v1, x equals v2, etc., then you can write the function simply as products of the factors of those. So let's see if we can create what they're talking about here. So this x-intercept, the root would be x equals 1, or the 0 would be x equals 1, or that x minus 1 equals to 0 would have been one of the factors that gave me that x-intercept. The second one The 0 was what? X equals 5, which says that x minus 5 was a factor there. And then the y-intercept at 0, 7, what that tells me is that's basically saying, let's make our function f. That says f of 0 is equal to 7, so that's giving me a point, okay? Now what up here about these asymptotes? What do those tell you? Well, remember that the intercepts, let's back up for a minute before I talk about the vertical asymptotes, that the x-intercepts were given by the fact that if a divided by b was equal to 0, then what that inferred to you is that a must have been equal to 0. In other words, the numerator was equal to 0. That's how I found my x-intercepts. So what that means is that so far what I know about f of x is f of x is equal to some factor a times x minus 1 times x minus 5. In other words, I know that these guys right here had to be the factors in the numerator. Now, there are going to be factors down in the denominator. How did I get those? Well, to get those, I take a look at my vertical asymptotes, because the vertical asymptotes occur when the denominator is equal to 0. So that says that x plus 4 was equal to 0 gave me one of my vertical asymptotes, and that what x plus 1 equal to 0 gave me my other vertical asymptote. I'm simply taking these and setting them equal to 0, right? So that down here in the denominator, that tells me that this is what? X plus 4 times x plus 1. All right, cool beans. So I've almost got my rational function written. The only thing I need left to do here is go figure out what that value of a is, and I get that by using my y-intercept, if I plug in those numbers. So I know that f of 0 is equal to 7. So f of 0 equal to 7 tells me that 7 has got to be equal to a times 0 minus 1 times 0 minus 5 divided by 0 plus 4 times 0 plus 1, which says that 7 is equal to what? Well, in the numerator, you got 5. There's an a in there too, excuse me, forgot that. The numerator got 5, and the denominator I got what? 4? Yeah? Yeah, negative 1 times a negative 5 gives me a positive 5, and a positive 4 times a positive 1 gives me 4. So that tells me that what? 4/5 times 7 is going to give me back my value of a, or 28/5 is equal to a. Okay, so my function f of x is equal to 28 times x minus 1 times x minus 5. Putting that 28 in the numerator, I'm going to put that 5 in the denominator. I'm going to get x plus 4 times x plus 1, and I'm going to leave it to you to multiply out the numerator and denominator. I'm not going to do that for you. Okay, that's enough of this amazing stuff for today, and I'm going to leave you to read the book and get going on the problems. I am not going to do any more in 3.3c. I did say I was going to do a video on that, but I'm not going to do that because I realized I wrote up all of the solutions to all of the problems on that, and I reread them and I thought they're written pretty well. If I'm wrong on that, let me know, and I will elucidate in the Q&A forum, or I'll do a video if need be. But read through the solutions on those, and that should help you with it. Guys, have a great rest of the week and the weekend, and I'll see you all on Monday.